In this video, I'm going to show you how to use the Z table and how to reproduce it on the simplest calculators, even simpler than the Casio calculator that you have, the FX991ES Plus. Remember, what is the Z table? It looks like this. It has the negative part for Z and the positive part for Z, okay? And each of these numbers that you see here gives you the cumulative area or the cumulative probability up to the Z that you have here. So the Z in this case is 1.35, so Z equal 1.35 means that this number that we have here is the area from negative infinity to this Z. Or you can say that this is the same as the probability that Z is less than 1.35. If we say that this is 1.35, the Z that we have here. This will be equal to the area that you see here. So it will be 0.9115. Remember that the area under the standard normal curve is exactly 1 if you go all the way from minus infinity to infinity. I will erase this and tell you something else. Calculators in general cannot, like some calculators can go from the Z score, so you give it a Z score and it can give you the area here, if this calculator is good enough. But going the other way around, having an area, so this is given, and you're trying to find the Z score, that is a little bit tricky to find on the calculator because you need to use some approximations. So as a student in Zayed University, you should be aware of research that is done by people on mathematics and statistics. I mean, whatever your major is, you should be aware that people do research. And this paper that I'm showing you here was done by a math professor. So this here, Alessandro Soranzo, and his undergraduate student, Emanuela Epure. And they did it in the University of Trieste, and this is in the city of Trieste in Italy. And it's a research university. This is a very good university. This is the title of the research paper. It was done in 2014. And you can find it online if you go to this website here. Okay, so now what did they do? They actually, before I start, I want you to see something here, is that they clearly mention that this is an open access article which permits unrestricted use, distribution, and reproduction in any medium, provided the original work is properly cited. So as you can see, I'm showing the paper and showing both their names here. So I'm properly citing their work. If you go to the beginning, at the beginning they define to you what is called the cumulative density function for the probability density function of the standard normal distribution. So this sounds like a mouthful, but I will make you understand it in an easy way. So I prepared this one-page document that actually summarizes the research paper. And first thing I want you to notice is the definition of the probability density function for the standard normal distribution curve. So this is the function, and the graph of it is here. The graph looks like a bell shape, and we know that this graph is the graph of the standard normal curve, And if you want to see it done using a graphing calculator, I also prepared it for you here. And it's the first one. I'm going to turn it on now. So this shows you the probability density function for the normal, standard normal curve. Now, just I want you to notice one thing is that the peak here is not really 0.4. It's actually 0.3989. And in order to see this, you come to your formula here, and instead of x, you put 0. So if you put 0 instead of x, you get e to the 0. E to the 0 is 1. And so the entire thing is just 1 divided by radical 2 pi. And this is the same number that you see here. Look, 0.3989, and what we found here was also the same. Just for you to see that sometimes when you look at a graph, you think that it's touching a point, but it's actually, if you zoom in, you see that it is not really touching 0.4. But because we wanted to zoom in a way that you can see the entire graph, that is why you had this misconception that it's touching at 0.4. This doesn't matter. Just for you to know that the formula that gives us this graph is the blue formula that I turned off and now on again. Okay, so this is what it is. Now the second formula that you see is the cumulative density function, or they call it the CDF. I'm going to show you here. We define it here. The CDF of the standard normal curve is the area up to a point. So it's the same as the probability that z is less than z0. So you first choose a z0. Let's say you choose this z0. Then all what this thing does is it computes the area from negative infinity all the way to your point. So it gives you all of this area here. Everything here has this formula that you can see there. It just tells you integrate the PDF function from negative infinity up to z0. Okay, so we can also see what this looks like. You notice, for example, that since that entire area, the entire area under the standard normal curve is 1, if you stop at 0, then the area before 0 must be 50% or half exactly. So let us see this in the graphing calculator that we have here. So the second one now, the black curve, is the area. So it asks you to stop at a z or at an x here, because this calculator takes x. And you see that at 0, look at this, at 0 the area is half. And as you go away from 0 to the positive side, you see it's increasing, and the y coordinate is approaching 1, as you can see. Eventually it will get to 1 at infinity, actually. But some calculators, because they're not strong enough, they can give you 1 even before you reach infinity. Also, as you are going to minus infinity, look at the y coordinate, it's decreasing. Of course, it's an area, so it's always positive. And it will be 0 when you reach negative infinity. Okay, so, but the nice thing is that most of the important part, or the important part of the standard normal curve, is between -3 and 3. The reason for this is that if you want to compute the area from -3 to 3, okay, this one here, from here to there, it will give you about 99.73% of the total area. That's why for the standard normal curve, most important part is the part between -3 and 3, since it captures most of the area. Now, in this paper, the paper that I told you about, that is done by these two mathematicians, the professor and his student, here also I show you what I just said in the previous slides. What they discovered actually is that this cumulative density function can be approximated by this exponential function. And notice that in this formula it has just one x. So inverting this formula is very simple. A person might ask, how accurate is this formula? Well, they showed that the error is very small. It's to the 10,000th digit. So the fourth digit, so it's accurate to three digits precisely, and sometimes you get also the fourth digit. And similar for the inverse of this function. They did it for x bigger than or equal to 0, this approximation, but because of the symmetry, you can actually get it for all x. And for example, the inverse, to find the inverse, I show it to you here. If you want, take a screenshot of this and look at it later. It just uses simple high school algebra that you took. Just how to go from exponential to logarithm. Okay? And the paper is easy to read for anyone who took a course in calculus before. What's important is, at the end, this is what's important about the paper, is that they give you the approximation of the cumulative density function and the approximation of its inverse. And they give you the approximations on certain intervals, but you can extend it to all of the interesting part that you're interested in using the symmetry. This is what I will show you now. This paper is about 10 pages long. It ends with an open problem that if you're interested, you can work on it. If you understand the paper, you probably would be able to solve this. And look at how many references this paper has. So the references are so many that, what is the last page, 22? So they have 115 references to this paper. So it's good work. This is good work that is done in 2014. It's recent, and according to the authors, and even according to what I tried to look up online, their approximations are the best known ones up to date, 2020. So in the sense that it's an easy approximation that uses one x and you can invert it easily. There are many approximations that exist in the literature, but theirs is the simplest one, and it's accurate up to, as we said, 4 digits, and that's what we need in order to replace the Z table. So now, all of what I said, even if you didn't understand any of it, it's still fine, because all what I'm trying to, the purpose of this video is to make you understand how to use your calculator to evaluate things from the Z table, so that you never have to carry the Z table with you again. And you can use the simplest calculator to do that. So first, I remind you of the things that we want to do. So there are two things. First one is, if you want to find, okay, so let's go immediately to the Z table, and then if we need something from the previous page, I'll go back to it. I'm going to choose, let's say, find the area. Let's say you want the area to the left of negative 2.78. Okay, so what is the area? We know it should be here. So it should be 0.027. I'm going to do something else. First, I want to show you something here. Actually, it's better to do that. the approximation that they had. It's important that you see the approximation they had. They approximated the cumulative density function by this formula for z probability of z less than z0 if z is less than or equal to 0. So what I want you to see now is the graphs. So if I graph the cumulative probability density function, and then I want to graph, let's go back and check, I want to graph for z less than or equal to 0, this function, which I have there, 1 minus 2 to the power, where is it? Yeah, it's immediately underneath it. So look at when I graph it. It seems like it's the same as the previous graph. It's approximating it well. Notice that it's approximating it well for negative z, when z is negative here. But when it's positive, you see that there is some difference there. And the nice thing is that if you take away this formula and take this formula now, and this one is the one that you see here. So let's choose a different color. This formula is for z positive. It's the approximation for z positive. And look, it does a good job for the positive z, and for negative z, it's not as good. Okay, it still can be used, but you wouldn't get accurate to 4 digits. So that's why you can use either one of these two formulas. For z negative, you will use the purple, and for z positive, you will use the red. And both of them are accurate enough. So, for example, if you, on your calculator, let's say, let's go back to the Z table, and I will remind you, we chose negative 2.7, let's say 6 or 8, I forgot, but it doesn't matter. And we want to compute the area to the left, or the cumulative area. So our Z is negative 2.76. So we want to see what's the probability that Z is less than negative 2.7, and the table is telling us it's 0.0029. If you go to your calculator, all what you have to do is write the formula, and I showed you this in the video on this formula that we made on how to use the Z table, part 1. And so let's go to negative 2.6 and see what we get. So ours was, it was the 2.76. I'm sorry for this. To go to 2.76 and hit equal, you get 0.002 and then 89, so the 8 becomes a 9, so 0029. Notice that it is the right answer. So if you want to choose another value, let's choose this value here that is coming from negative 1.65. So negative 1.65, we'll put it here, 1.65, and you will get 0.0495. So 0.0495, correct. If you want to see something from the positive side, just choose anything. Let's choose this number here. So this number is coming from 1.97. So let's put Z. Remember, this formula, we have the Z, this number here, and we want to find the number here. So let's check. If we put 1.97 in here, so 1.97, hit equal, 0.9756. 0.9756. So now you know that if you are given Z, you can use your calculator to find the cumulative area to the left of Z, or as you know, it's the same as the probability that Z is less than your Z0, your Z score Z0. And now the better part of this, and in some sense easier to use on calculators, even the older calculators, is what if you have the area to the left and you want to find the z-score. So in the Italian paper they found this formula when the area is from 0 to half, and they got this formula for z0 when the area is between half and 1. You know that the area under the standard normal curve is from 0 to 1. I mean, it's because it's a probability, yeah? Any probability is between 0 and 1. And so let us check these two formulas. This is what's important now. So how about we just use the same numbers that we used before? So right now I'm going to enter, let's enter this number here, 0.0495, and we need to enter it. So let's see. This should be entered in the formula here. Okay, so this is the formula when the area is between 0 and 0.5. So we chose 0.0495, and that's less than 50%. It's actually 4.95%, so much less than 50%. And so we use this formula, okay? And this formula is easy to enter in your calculator. You can take a screenshot of this and then put it in your calculator. All what you have to do is to put the area here, okay? So again, our area is 0.0495. So we will put 0.0495 and check what it will give you. Minus 1.65 for the z-score. So let's see. Minus 1.65. You see, minus 1.65. If you want to check, okay, let's check another one quickly. We will just choose a trend, this one. So 0.2546. 0.2546. It's giving us that this is coming from the z-score. For the z-score, you do to 2 digits. So this is negative 0.66. Negative 0.66. Let's check. So this is coming from negative 0.6 and up also 6. So this is great. Let's go to the positive side of the table and choose at random. Okay, so choose this one. 0.6700. 0.6700. So this is giving us 0.44. So let's see, 0.44. Yes, and one more. Let's choose this one here, 0.9934. 0.9934 equals 2.76 if you approximate. So this will be, sorry, 9934, 0. I am sorry for this. I'm actually using the wrong formula. I mean, near 0 it will work, but the formula that we should use is this one. Yeah, it's good that I made this slight mistake so that you never make it, yeah? And so remember, I was using the formula that is for the area between 0 and half. So now I'm going to use the formula for the area between half and 1. So let's put this one again, but in this formula. And this formula, I have it here. Just one second. Yeah, this is the formula where you enter the number immediately here. You don't do 1 minus. Okay, and so 0.6700, 0.6700, it will agree, of course. So you get 0.44, as you can see, to 2 digits, which is 0.44, correct. Now let's do this one, 9756. So 9756. This is coming from 1.97. 1.97, as you can see. And let's do one more just to, actually the one that we're doing is 9934. So let's do 9934. This is coming from 2.47 to 2 digits, yeah? So 2.48. So yeah, so sometimes you might get just a little bit of a difference, because if you notice here, the numbers are very close to each other's here, so it wouldn't make a big difference. Let's see if we put 32, would we get 2.47 also? 32, 46. Yeah, so let's see if we put 9927. 9927, 2.44. So it is 2.44 correctly. You see, yeah, there could be a problem with the last digit, but it's this is so minimal. The approximation is very good. From I would tell you, from negative 2.3 to 2.3, if you take any area, those are the Z scores, then you will get the exact number to 4 digits. But then, as you know, for the paper here, when they made the approximations, they didn't tell you that we did the best. It still was to 10 to the power negative 4. You know, so you expect in the 4th digit after the decimal that there could be a little bit of a difference. So if you want always to 3 digits, you will get the right answer. And one nice thing for you to see before I close is this. If you want to check that these two functions are inverses of each other's, I just want to talk to you because students like to see these things. How to check that two functions are inverses on a graph? You just graph the line y equal x and check that they are mirror images of each other's. Here you can see clearly that these two are mirror images of each other's, and the other two are also mirror images of each other's. Remember, what are these? What am I putting? I'm putting the formula here. So let's erase this quickly, and I remind you that when z is less than or equal to 0, we use this approximation for the area to the left of z0. And if the area to the left of z0 is between 0 and half, then z0, the negative one, yeah, it will take this formula. On the other hand, if z is 0 or bigger, then we can use this very simple exponential function to approximate it. And the inverse of that is that if the area is between half and 1, then the z0 is here. Okay? And at the end of this very short page, I give you the reference, which is the paper by Soranzo and Epure. Okay, I hope that this video helped you somehow understanding that this whole Z table can be replaced by a simple calculator up to the 4th digit for area. But if you are within negative 2.3 and 2.3, which I want to just let you know something about, if you are between negative 2.3, so for example, negative 2.3 and 2.3, you capture about 98% of the area under the curve. So this approximation is really good. It's very good comparatively to other approximations. Okay, I hope that this video helped you, and I'm going to make more videos for you to benefit from. And if you like this video, please like it on YouTube.